Hello? Oh, yep. Great. So, um, apologies in advance if this is okay. If this is anyway, what I've put here are some questions that I've been thinking about, right? And so so if I put them up, I guess we're all going to think about them, right? So, and this is, I mean, I guess my exposure to the Magnon area is a little bit narrow, so these are maybe a little bit self-centered questions, so I apologize in advance for that. But so one thing, so with our erbium gadolinium vanadate work, right, we've got a gadolinium vanadate crystal with a very small fraction of the gadoliniums replaced by erbiums, and then we look at the coupling between the gadolinium magnons and the erbium, right? And as I showed in my talk, right, we had a reasonably successful model for explaining the spectrum we saw if we took the erbiums and sort of magnetically, I think it was magnetically, coupled them, or via exchange, coupled them to a thing we called the gadolinium magnon, right, which was the same, which was something that tuned the same way as our magnon mode that we'd seen in our microwave experiment, right? But of course, the thing that the gadolinium's going to, the erbium's going to talk to is the kind of the gadolinium nearby, right? And this gadolinium is going to be in a quite different environment to the rest of the gadoliniums because it's got a big erbium sitting next to it, right? And so, so we've sort of made a hole in the gadolinium lattice by putting the erbium there, just at the point where where it's coupling, and that coupling is kind of strong compared to the coupling of that gadolinium and its other one. So I guess we've kind of glossed over this effect, and does this matter? And how do we model that situation, right? And then a little bit going forward, if our current, and this isn't in the talk because it's all a bit sort of waffly, right? Our current understanding of where we are with doing magnon mediated transduction with our current host, I guess the first thing to say is that we have tried to do transduction with erbium and gadolinium vanadate, and we saw it, but only because I had a student that wasn't going to take no for an answer. So the amount of transduction was so tiny, right? And and it certainly was about the same order as you'd expect just by having the erbium dopants in a non-magnet host, right? And this might be because we couldn't tune the microwave driving field and all these other things, right? But it might be because the coupling between our erbium and our magnon sounds big, but isn't, right? In the sense that if you were to put one photon's worth of excitation into the magnon mode, then that only very, very weakly excites each individual gadolinium, right? And so that means that you need to, and this is sort of in Tania has a expression like this in one of his papers, right? You take this 11 gigahertz and you divide it by the square root of the number of ions, right? Or in this case, the number of irons, and in our case, the number of gadoliniums, right? And if you do that, then the coupling goes down to sort of about what you would get just by driving the spins directly, right? With a microwave photon spread out amongst that level, right? And so we're in a situation where we've got microwave photon, magnon, and that coupling's huge, right? And then magnon to the rare earth, which the coupling sounds big if you express it in one way, but if you divide it by the right factor, then it all of a sudden becomes quite small, right? And so one way to make those, to kind of make that situation better would be to have small magnets around each erbium, right? In this case, so you have so when you divide by the number of gadolinium square rooted, then you're dividing by a lot less number. That would give you less coupling between the magnons in the cavity, but that's so huge anyway, we don't care, right? And so the question is are we going to get a localized kind of magnetic excitations around the erbium, and is this something we can use, right? So that's okay.
Lots of questions. So, thanks for setting the kind of a framework of this, and I think you pointed to a lot of the challenges that are involved in this. So, if you were to pick one question that you could ask the magnetism community, what would it be?
So I've got more slides with questions. I've got lots.
Okay.
But
from this slide,
but
what's
from
the
this
most
slide
important question?
Are localized magnons around an impurity something that people have studied before?
Okay. Anybody want to? All right.
I have there a very, very naive picture, and I will get crucified within 30 seconds. So my picture is basically linking to general solid-state physics for this problem.
Yep.
So I would argue that I naively would expect something like free death oscillations or Kondo effect-like physics, where you have a magnetic impurity in an environment, and the environment is called now magnon. So in principle, if you would depict this in a band structure, you have a kind of singular defect. The defect is basically distributed over K-space, so whatever there is could couple to, but you are limited in K-space with the interaction. And this should kind of give you a picture like Friedel oscillations for RKKY interaction or something like this for the interaction. That this would be my picture I would put forward. And now I'm looking forward for your insights.
So I'll sort of follow up and ask: Is the material you're looking at conductive or insulating?
It's insulating. Yeah.
Okay, good.
And so the free electrons, like don't.
You don't want them.
We don't want those. No.
That's the charge noise, right?
Yeah.
Okay.
I merely have another question that I would like to add to yours. You're asking, can we have localized magnons around the erbium? And my question is, what do you mean by localized magnons? I mean, you can have magnons which don't propagate, or you can have magnons which are very short-lived and so only live in the vicinity of the erbium. Which is the idea that you're talking about?
I mean, I think we want magnons that are. We still want them to be kind of narrow, so we can. I think we want magnons that don't propagate,
Okay.
like that are. So, yeah. So, like, we want something that has the advantages of a magnon, i.e., that there's a whole lot of spins locked together, so that there's a big G factor to a big effective magnetic moment to couple to a microwave mode, right? But we want the erbium excitation to be a significant part of that magnon, which kind of means that you want them small. Yeah. So, and it seems to me that would be a thing that you would have. Yeah.
Yeah, so I was wondering, the coupling mechanism I could understand as I have the magnetic field, which is given by the magnons, right? So you have magnetic field fluctuations, and this is coupling to the magnetic moment of the erbium atoms, right?
Yep.
And then you would write this as some integral over the density of states that your magnons have, right? So then, so my, it's, so I'm not sure if, so you have a point emitter or a point impurity in an extended mode. So even if you localize this mode a lot, I mean, it's still a point emitter so it's the value of the magnetic field at the point, and then the density of states that matters. This is what I would.
Yeah, so unless there was some sort of resonant mode around the erbium that was somehow out of separated from the normal band of magnons, and therefore
I mean, in principle, you could have some symmetry effect that makes it not part of that, but that's probably hard, I think. I don't know, I usually think about my zeroth order approximation for magnons is, I know many things about phonons, and I'm just going to pretend that they're kind of like phonons. So if you put in, different spring constants for an atom that's sitting in a lattice, then I would expect that I would have, some kind of localized mode that's out of the phonon band, but then it just has interaction with just a few of the atoms around it. It's usually very localized. Then you probably give up your coupling to the microwave cavity. And then you have a mode where the atom moves with all the other atoms. So, this is particularly in the case of of the magnet, of the ferromagnet, sort of simple model of the ferromagnet, then the erbium will move as part of the uniform mode, because that's sort of a natural thing to do.
Yeah, so I think that's exactly the way I was thinking about it too, right? Is there something like a localized, like, vibrational mode around the erbium that's in the
Sure.
gap of the
Yeah,
components?
I mean, so that this would be, so in various communities, this is sometimes called the magnetic polaron.
Okay.
To bring back memories for some of the people over here. Some good, some bad.
Yeah, I have just a very naive question, which is, wouldn't you be able to see this spectroscopically if you just look at transmission in the microwave regime? You should see absorption at a well-defined frequency for these bound states, and that don't disperse.
Yeah,
and then you
yeah.
should see a continuum at a different range of frequencies for all of the bulk
Yeah.
magnons.
Yeah,
do you see that? Or
Um,
can you see that, or can you not see that?
Should we bring up the some of our? We see. Where is it? Just wondering how much structure is on the results that I showed. There's certainly not much. There's we see these things coming down. Yeah, no, it's not really visible on that graph. There are some fine features. There is stuff there that we think is maybe kind of ground state structure in the gadolinium, right? That come down with this. That's right. That's right. We definitely.
So your magnetic field effectively only couples to the k=0 mode, and then you don't really see the absorption.
Yeah,
You'd need to have a spatially varying magnetic field that would wiggle. to
Yeah,
excite
and
the
I
other
mean, I think
magnons.
you might expect to couple to it with the k0 mode, but because our concentration of erbiums is so low, then it won't be very easy to see, right? Because remember, this is only the trace of erbium that happened to be in our, so this of the order of 1 part per million, right? We can see some other EPR lines in this that we think are neodymium dopants, right?
Okay.
And then they've got a G factor that sort of works for neodymium, right? But those can kind of be understood as individual neodymium atoms. And that sort of makes sense because the same company that grows this grows neodymium doped
Is
GVO.
there any hope to spatially modulate the power of of the microwave field to kind of probe a different K vector? And then you presumably, if you could do that continuously, you would see a continuum of excitations at different energies for the band.
Yeah,
and just
I mean,
one
I think,
energy for the isolated excitation.
I mean, I guess our Ks are very, very close to zero, right? With microwaves.
I mean, you've got a centimeter wavelength.
So I think I think Bill's probably thinking about antennas and launching microwaves and such, which is how one does it, right?
Yeah.
I have a question regarding your discussion. So I will kind of allude a little bit what I see in this picture.
Yep.
So I see an antiferromagnetic resonance line coming from higher frequencies,
Yep.
moving downwards in frequency for increasing magnetic field strengths, and it interacts with some microwave resonator.
Exactly. Yep.
You see no erbium or rare earth in that
That-
at all, I would suspect.
That's correct. Except we see if we go over here, right, we see a few things interacting with the cavity at quite different magnetic fields that we think are neodymium, right? In terms of identified, partly because we expect there to be more neodymium than other things, and partly because of the G factor as it tunes through the cavity. Right?
I see. And,
Yep.
but
no erbium.
But my argument would be then this is potentially not the ideal experiment for testing this. I would go for more broadband microwave spectroscopy
yeah.
perspective, and then check where the erbium EPR lines intersect with the antiferromagnetic resonance that you would see if you're not coupling to a confined cavity mode.
Yeah.
And at this location, then they're at least resonant. And if you see that either the antiferromagnetic resonance line width changes or the EPR line width changes or both or whatever, then you see, or then you at least can quantify your coupling between the two.
Yeah. No, that's a good point. I mean, I mean, one nice, quite broadband way. So people, you could think of putting this on a waveguide, right? I think there you would, if you wanted to see something with erbium, you'd be even more limited by the fact that you don't have very many erbium, right? And so that, no?
But the erbium resonance is like completely off scale here at these fields, right? The magnetic, is this along the G equals 12 direction?
Yes.
Then that's 180 gigahertz per Tesla.
Yeah,
right?
so you expect to see it sort of over here. Sort of.
10 millitesla is where you would see the crossing of the line. So I guess what we're asking is, what do you see there?
And I'm not. Yeah, we see some stuff.
You see stuff. Oh, well, I mean, there'll be
But
lots of other things besides erbium there as well.
Yeah.
So, but that's,
Yeah.
I mean, whatever you see there is probably very interesting.
Yeah, no, what? Yeah, we see stuff we don't fully understand, I guess, and small coupling as you'd expect from a
Yep.
purity.
Yep. Well,
I mean,
but at least it's resonant, right?
Yeah.
So if it's there,
Yeah. Well, one thing that one idea you've just given me. One very nice thing about the rare earths is you can do what we call Raman heterodyne spectroscopy. There are all these ways of doing spin spectroscopy using optical readout, right? And that has the benefit that it's sensitive, right, in a way, because you're detecting optical photons, which are essentially big things. But it's and it's kind of broadband, right, because you don't need the cavity's narrow Q to get a signal. But it also means that you can, which rare earth you're talking to, because if you shine the light at an erbium frequency, you're not going to get any signal from neodymium and vice versa. So that's probably that's certainly something to take home, right?
so now I guess I also understand why the erbium is aligned with the magnetic field, because the energy scale for that is going to be huge at these fields compared with when you look at it optically.
Yeah.
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 Carlos has his own individual
Can I
one.
go back to I want to go back to the basics here. You implied that so first of all, why is it a hole? And can you make it not a hole, like an electron?
Oh, so I don't mean that sort of hole. I mean, you've got a lattice of gadoliniums, right? And you've disrupted that lattice of gadoliniums by taking one gadolinium out and putting an erbium in it, right? So a hole in the sense that you've...
So it's just a
substitute.
vacancy, you mean? It's not
Yeah,
a hole
I
in the
mean-
sense of the electron, the
Yeah, no,
electron
exactly.
hole pair.
And it's not really a vacancy either, right? Because you put an erbium in the vacancy, right? So, but it's yeah, bad word perhaps, but it's certainly a disruption in the lattice, right? Which is
So, but when you remove that, that's an insulator? I thought it was a metal, gadolinium.
I know it's gadolinium vanadate, right? And so we I guess the vanadate's important because they stop it being a metal, but other than that, kind of just a spectator, right? So we have this lattice of gadoliniums in the crystal and the erbium, and the vanadate's not doing very much, which I guess why it's not mentioned, but it's certainly an insulator, right?
Okay.
Yeah, I think in the way the gadolinium orthovanadate is sort of the perfect magnetic structure in a way. So the rare earth orthovanadate with all of the sp and the d electrons, it's guaranteed to be insulating. It's a nice wide gap insulator. And then all the changes as you go across the rare earth is how many 4f electrons. If it's yttrium, you have 0 4f electrons, so it's inert, and that's why you tend to dope it. If you have the gadolinium, then you have the half-full F shell, so it's just a pure big spin with no orbital character. So that's also a nice example to look at. The other ones that are kind of fun are like cerium, because then you have the 1 4f electron, or the ytterbium, and then you have the 1 4f hole.
Maybe my question goes in either to you or to Mike. So is it clear if this is a magnetic dipolar interaction, or is it Heisenberg-like? Because if I remove a gadolinium out of the vanadate lattice and place an erbium in there, the erbium, it's in the 4f shell, the spin. So it's decently well protected from the environment. That makes it very attractive in terms of optical properties and also in terms of magnetic properties. So it's clear how the coupling mechanism actually works.
So, I mean, this might not be answering the question. I mean, so normal magnets exchange is what gives you the ordering, and then you forget about the magnetic dipole-dipole, right? In this case, both effects are there, both an exchange interaction as well as a magnetic dipole-dipole interaction, and they're in this material probably of similar magnitude, right? In that so there's exchange coupling between the gadoliniums as well as the fact that they're magnetic dipoles, right?
So on a related topic, we have a preprint up on the archive looking at magnons and erbium oxide. Yep. And erbium oxide has an exchange interaction, and it also has a dipolar interaction, which is long range. Exchange interaction is exponential and short range, a little bit larger. Dipole interaction is long range. The magnons are definitely very different if you don't consider the dipolar interaction, that long-range dipolar interaction. And it's sort of related to this aspect of what's the size of the effect. The Néel temperature is 2.5 degrees, so that's kind of where that transition is roughly.
Yeah. So we actually have some erbium oxide results that we should maybe look at.
Oh, fantastic.
They were taken. I mean, there was a while at the start where it was like anything magnetically rare earth would throw it in the fridge and make some measurements, and with the erbium, yeah. Anyways, well, I can't. We didn't make much sense of it, but now that you have made much sense of it, maybe our results will make sense. Right? So we'll have to have a look.
I just realized that I still have a problem to understand this magnon in your material. If you have a real antiferromagnet, so in principle you have no magnetization. How do you couple to the magnon? Do you break the symmetry already, or how do I have to imagine this? Yeah, sure, if you go through the spin-flop transition, then you can do it. But then is it just this minimum magnetization which is precessing? Is it still important that I have an antiferromagnet? So that's what I would like to understand. And I mean, 1 Tesla is not so much for a spin-flop transition.
Yep.
Did you measure the magnetization of the material in this field?
We certainly haven't made magnetization measurements. There has been work that preceded us. We're looking at the magnetic phase diagram. So we were sort of, if we look at this picture phase diagram. Where is it? Oh, come on. Or maybe it's. Yeah, I guess this diagram is for, I think. No, that's. Yeah, so this is for GVO that comes out of a paper that's not ours, right? And so how that was established is, I'd have to go back and have a look. But I think the magnetic ordering as a function of temperature is, at least we've accepted what other people have come up with there. I mean, in terms of how you get a magnon in an antiferromagnet, the way I think you've got spin up lattice and a spin down lattice, right?
Mm.
And you apply a magnetic field, right? And at zero magnetic field, these two things are degenerate. But if you apply a magnetic field, then each of these, every half of the one sublattice is off resonant, and so it's basically just a static magnetic field that is certainly, there's no global magnetic field, but locally at the other sites there definitely is, right? And then these spins, this kind of layer of spins all precess uniformly in that mean field produced by the other lattice. Right? So.
Okay.
So there's two modes.
Mm.
I mean, I think of them as each mode being just a separate lattice, but that might not be the right picture. But there's certainly, as you put a big enough magnetic field, then the resonant frequency of these things become far enough apart, then you'd think the mode was going to be all one lattice and all the other lattice, right?
But then again, the domain size would be very important because there you change the sign.
Yeah. But in terms of, the domain, yeah. Like if the domains are big enough such that what's happening around the edges of the domain you can forget about, right? Then I think it's the fact that there's no kind of long, yeah. I guess the interesting thing about the different domains is that your two options for how this thing orders, right, are pretty limited, right? That they can either order like this or like that, right? So the difference between domains isn't going to be huge, right?
So I think all of these questions are kind of going on the same theme. Yep. Related to how you couple into the magnon with the spatial variation of the magnetic field amplitude.
Yep.
So basically, I guess, I don't know how your setup works, but if you have any kind of rapidly varying component of the amplitude of the field, away from your resonator in fringing fields or something like that, and you should be able to excite things even
Yeah,
at very short scales with some
um,
amplitude.
like part of the reason why we got into the ultra strong coupling regime is that, I mean, we use these loop gap resonators, right, which have it's in some sense like putting the sample in the currents that are creating the magnetic fields are basically solenoidal, right? So you have a very
It's very uniform.
very uniform
Okay.
magnetic field, and quite. And because the magnetic field lines sort of bunch up as they go through the
Okay,
solenoid and
I
spin
got
out,
it.
they have a good filling factor, even though
Okay.
So
Okay.
so we went to some. I mean, and these were. I mean, we put some effort into thinking about what was the right thing to do there from when we're doing the transduction work, right? And so, yeah.
Thank you.
Yeah, so it was just to complement the question regarding the magnons and an antiferromagnet. The one way of seeing this, you can, I mean, there are no static fields, right? But if you excite the system, you can get fields because of the excitation. And one way of seeing this is to study the dynamics of both the magnetization and the Neal vector. And they will be coupled, right? And one of the two will couple will give you the fluctuations that couples to the spin.
I think that's related to this issue of resonance and off resonance. So
Yeah,
one
right.
of the sublattices is resonant, it responds more. The other sublattice is off resonant, responds less. Hence, you end up with a net magnetization as
Yeah.
part of the response.
So my other question.
You said you had other questions, but
Yeah, my other questions. There may be the questions are less long, right? So you know, with the rare earths, we have this. Our optical inhomogeneous line width is narrow compared to the energy scales that you know spin interactions, and our homogeneous line widths are much narrower, right? So are the rare earths useful probes for magnons and other systems, right?
yeah, so I will make a comment here, which is I think almost certainly yes. The thing that I think is characteristic about the rare earths is that they're relatively slow. So if I were, this is my opinion.
Yeah.
So I would think that conceivably they could be a good, you know, like a local spin thermometer. If you have a temperature of magnons around, maybe the characteristic, the optical spectrum might indicate what's going on there, or some other non-equilibrium spin dynamics in the area. I think that would be really cool.
Yeah, and so by slow you mean that they would struggle to look at fast phenomena? Is this the
No, I mean, just they would. I don't think that's true. I think that they have a good frequency response, but I don't think that you can. And maybe this is a misconception here, but I just because the line widths are so narrow, you know, you have 100 kilohertz line width, then you're only going to see things
it happened? Yeah,
you know that happen that slowly, and a lot of things that are happening in these systems have, you know, nanosecond scale or 100 nanosecond scale, and I think that might be you'd probably have to pick the rare earth. Maybe erbium is not the right choice because again, this is part of the thing where people get driven towards particular rare earths because they want lasers, and maybe they're not the right choices for some of these other things.
yeah. I mean, I guess the thing that can so each rare earth is narrow. The ensemble is quite a lot larger, right? So we can certainly take light pulses into the rare earths that are short, and then you know rephase things and get them to be spat back out again. So I think you could, but I guess that
Like optical memories, essentially.
yeah.
is what okay, I see what you're saying.
And so, but I think that what that would require is triggering something, right? You've got some time.
We
that
have
you can
high-speed electronics, right? That's okay.
I would like to add slightly. So the effects of rare earth impurities in the fruit fly of ferrimagnets, meaning yttrium iron garnet,
Yep.
was kind of decently studied. I think 60s, 70s or so. There are a lot of additional relaxation effects, slow relaxers, fast relaxers, Kazuya LaCroix or whatever.
Or back transitions.
So it might be good to have there a look what people have actually done.
Yeah.
I'm not aware of any optical studies which link us to optical properties. So this might be really, or I think this is the very interesting question that I would ask. So is this kind of similar to NV centers and magnons? Is this the alternative route in order to do spatially resolved magnon studies in magnets?
Yeah, I mean it could be, right. I mean the nice thing that NVs have is that you can spin polarize them optically at room temperature, right? And we don't have that, so all our nice interesting properties are only around at low temperatures. The NVs are of course an allowed optical transition, so they're a lot brighter than a rare earth. So you know, you could seeing a single NV is much easier than seeing a single rare earth, right? But you could what we can do, the many rare earths you've got are very effective ways of bleaching them out, right, by optical pumping to different hyperfine levels of the rare earth, right? And so in that way you can imagine doing things like with lasers coming in at two different angles, right, and then making a grating, and then changing the pitch of that grating by changing the angles, and then probing things in different length scales that way, right? So I think in terms of a scanning probe microscope, it's probably not I mean, I don't think we would compete with NVs, right? But if you had in terms of having a rare earth doped crystal and playing some kind of spectroscopic tricks to see things on different length scale, that could be something that would be interesting to do.
Some of the first measurements of spin diffusion in solids, particularly semiconductors, were done in exactly that way,
Okay.
making a spin polarization gradient through excitation and then watching it decay.
Okay.
Other thoughts about this one, or shall we go on to the next slide? All right.
Just maybe silly question, but then how? So these NV centers, right? They put in a tip or they sprinkle them over. So how would you?
What would you do with the rare earth?
Do this?
You would get a rare earth crystal, say, and then sandwich it on the top, right, and then do the spectroscopy on that sample, right?
So you would just see the stray fields, and then it should be, but then it should be a very thin. Is that enough, so to say, that if you have the crystal and I don't know, just curious.
Yeah, I mean, like what you can play all sorts of tricks with turning your supreme spectral resolution into other sorts of resolutions, right? So with things like magnetic field gradients or structured light, essentially. And so, I mean, if the sensitivity needs to be in a very thin layer, you're only interested in what's happening in a very thin layer, then you could make the sample thin, or you could try and do something such that you're only seeing signals from the rare earths which are close to the surface, right? And things like evanescent coupling might be a way to do that. If there's a, you come in from the magnetic side of things, and with total internal reflection, and then you'll only excite in an effervescent way the rare earths that are close to the boundary, right?
There's some really nice work on rare earth containing molecules that can be sprinkled pretty easily. So they're very stable. Things like erbium, HVAC is one that, again, the chemists have sort of magically come up with some of these. The issue always, though, is that diamond, no spin orbit interaction, vacancy, nothing, nitrogen, not very much, and nearly no nuclear spins. But with the rare earth systems, the spin orbit interaction is gigantic.
I mean, is there anywhere that's a
That's
a
avoidable?
good thing, or
it's a. So okay. So now we're going into my opinions on this, but I do not see rare earth sensors as being ever relevant in this kind of context at room temperature, because of that reason. And so then the question is, what is the interest in sensors that aren't operating at room temperature? It's a very, very tiny niche, very, very specialized.
No, I would.
So.
I mean, I would 100% agree that it's hard to see how. I mean, the hotter than about 5 Kelvin, it's not worth getting out of bed, right?
Right. So, but I mean, if you are doing things, I mean, if it's for quantum, right, and so you're going to operate in a, sub 1 Kelvin, a lot sub 1 Kelvin, then as a sensor, that's sort of the statement that is the detector, and so it could be useful for readout. And then, sure. I mean, you have a narrow line width. Your shift in things in response to some field is huge because of the large spin orbit interaction, and then it's easier to detect. So that makes sense. Quantum radio in space, so I don't know.
So I guess another question is: are there other applications for this sort of antiferromagnetic resonance in the regime that we're looking at? And then, I mean, I guess so our antiferromagnetic resonance spectrum looks something like this, right? And what's kind of nice is that this isn't very big, right? And so I mean, it follows on from what we're just talking about, that if that's going to limit things, right? Is there a way that we can break this relationship between ordering temperature and the zero magnon frequency, right?
Yes. I think Hans.
Yes. So for me, this frequency point is a square root out of the exchange energy and the anisotropy, which is semi-phenomenological. And so all you need to do is, so you want to have the exchange high and the anisotropy then sufficiently low, and then you can, in principle, engineer this if you have control over your material. But so my experience there kind of boils down to the fact that you need to select the materials correctly, because these are all built-in properties. So this temperature, or the frequency and the ordering temperature are decoupled for me.
Okay. But I guess ours is small because we've got a large part of the reason why ours is small is because we've got a small ordering temperature, though, right? I mean, small exchange, which gives you small ordering temperature.
I would say, small exchange gives you small ordering temperature, but in principle, I would say that you can keep the exchange large and you can compensate with a very weak anisotropy field. And if you have a very weak anisotropy field, then this point should reduce accordingly.
And that's that's a matter of finding the right crystal. Is that the...
Yes. I guess so, or yes and no. It depends which community you would ask, I suspect, because if you want to have it then insulating, then you're basically limited to the crystals that have been researched. If you are opening yourself up into the direction of synthetic antiferromagnets or something like this, then you could be, in principle, engineer this point, with the caveat that it's then not clear to me how the parameters which are built into the constituents, how they affect the damping. Because you will implicitly search for low damping.
Yeah, so I'll make a comment here, which is that the materials are usually driven by whatever the interests at the particular time prior were. And so that's partly why you hear about the conducting materials. And, in that sense, the picture was generally, I want a conducting material so I can drive spin torque through it. And I'd like a low magnetization so that it doesn't take that much spin torque to shift it. So it's all based on magnetic random access memory or things like that, or high-speed logic. So, yeah, but it's always going to be my magnet better conduct. And so it's all of that materials exploration is entirely orthogonal to the interests that we now have, because we want nothing moving in the charge channel ever, please. And so YIG was something people tolerated because it had such great properties in other contexts, but they would complain about how it didn't conduct. Only now, the last 10 years maybe, the interest in doing things without the...
I would like to comment. So YIG and derivatives of YIG, like doped YIG or whatever, they are all kind of heavily researched for microwave components like circulators, isolators. And this is basically all the radar technology that is used nowadays heavily, leverages on this know-how. And these are non-conducting materials because of damping properties, but this is the origin of this material, so to say. But there's...
Yeah, which also means room temperature, because you want your radar to work at room temperature. Yeah, but I mean, that's fun. That's sort of the classic thing about materials, is that you have a really new type of application that you're looking for. And that's when the people who are around and know all the failures in the field become very popular, because you say, tell me about a material that, you didn't look at further because it had this, 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 and this, and you said, I don't want it. So.
All right, and then the last question I have, and this is would be, I mean, I haven't read the papers in as much detail as I perhaps should have, right? But there are these stuff that's come out recently with magnon-phonon couplings and magnon-phonon hybridization, and that's of course interesting for optical transduction, in the sense that, because the people who look at acousto-optic stuff like to call acoustics the universal transducer, right? And so this magnon-phonon coupling is, I guess, a obvious precursor to magnon to optical transduction, right? And so question is, what are the prospects for that? And and then the other one is because the self-interest bit is can the rare earths help here, right? And so one thing that this galphanol and terphenols and stuff, the fit is iron, right? But all the other letters in there are mostly rare earths, right? And so they have large magnetostrictive properties, and so
So I'm going to make one comment and then turn it over to Hans. But it's my one of my collaborators over time was Jos Heremans at Ohio State, and he would always make the point that there's no such thing as a phonon diode. So, if you've got a solid, the phonons will always move through from one to the other. So the kind of nice thing about magnons is that you can have non-magnetic materials, in which case the magnons do not go there. And that can be really helpful.
But, there are these phononic crystals, right, that have that.
Yeah, the quality factors are, that's really hard. Yeah. It's not broadband also, right? So, yeah, certainly not.
So I agree with your statement. Phononic crystals are hard, and it's about selecting modes. The phonons are still around. My top-up question: are you thinking implicitly quantum here, or in general?
Yeah, that's a good point. I guess I'm usually thinking quantum, right? But that doesn't mean to say, like, I think, obviously microwave to optical conversion is something that's done every day, right? Whenever we use the internet and all those things, right? With very low quantum efficiencies, but they don't care too much, right? But there's if you offered someone a more efficient EOM that I think there's as I said at the start of the slide, people doing superconducting logic, right, are interested in microwave optical conversion just for the engineering of their system. It's if you can get the stuff down to lower temperatures with fibers and then turn it into electronics, that might be better than trying to connect coax down to your low temperature thing. So I think it's worth thinking about the classical ones, but I guess I think about quantum stuff most of the time. So. And of course that's kind of easier, right? Because I think the bandwidths you'd need to have to be compelling are a lot lower than if you're trying to make a telecommunications network, right?
So if you're thinking about quantum, my generic answer is, so there are various approaches out there besides magnon, phonon, optical transduction.
Yep.
And I'm thinking about optomechanics combined with superconducting circuits, like pursued by NIST Boulder.
Yep.
Or Boulder in general.
Yep.
I think the efficiency will dictate. So wherever gets, or whoever, or whatever system gets to kind of decent efficiency first will basically win this race.
Yeah, the Boulder people with their, they got to high efficiency, right? But everything else is a bit rubbish, right? In terms of the beautiful experiments, right? They have these membranes, right? These very thin, I forget what it's made of, but high stiffness membrane, right? And then they couple to this membrane, so it's got maybe 100 kilohertz resonant frequencies or something like this, and they couple to this membrane with a capacitive coupling as part of a microwave resonator, and then send a laser beam through it, and as it moves in the mode, then the problem is a little bit twofold. One is that the bandwidth is quite low because the Q of this optical resonator is the line width is very, very low, right? So they can transduce with kind of kilohertz type bandwidths, but not a whole lot more. And then the other thing is, it's like the noise properties aren't great either, right? I mean, I don't want to sound critical, right? Because if you've got an efficiency of 10 to the -5, it doesn't matter what what your noise properties are like. But but the fact that you can't cool this mechanical resonator down to its ground state is an issue. It's something they would argue that they can get round a bit, right? And then the other thing on the microwave side is it's sort of like a 4-wave mixing. So you've got 2 microwave tones and 2 optical tones, right? And so you're kind of driving things hard in the microwave regime as well as the optical regime, and whether that causes noise problems too. So yeah. So I mean, they were the first people to get good efficiencies, and I still don't think anyone's got close to as good efficiencies. But I don't think it's the final answer, right?
No, I agree with you. So it's not the final answer. So my last recollection was, I think, around 50% or so.
Yeah.
Which I find impressive, and you pointed out the caveats. Certainly, I'm a fan of Magnon Phonon, I have to say.
Yeah,
Thanks to Sylvia. But I also know that the Magnon Phonon field, so the vision which was put forward by Sylvia and Georg and others, is to realize a basically phononic, photonic, and magnonic crystal, which co-localizes the excitations, and this is technologically, I wouldn't say impossible, but it's not trivial. Let's put it like this, and therefore, even if we can argue that the efficiencies could reach unity, I, as an experimentalist, have to say that I would like to demonstrate this. So we are not there. So
yeah. So I mean, from that, yeah. Anyways, I mean, if the challenge is getting magnonic, phononic, optical, maybe having a rare in there which might, get rid of the need for an optical resonator of the same, same quality. I mean, the one thing that Andre kind of schooled us a bit was that we were silly to be trying to do stuff with transactions with high quality optical resonators, right? Because he had an optical resonator in his transaction experiment, but it was essentially just Fresnel reflections, right? It was a very low Q resonator, right? And the experiment would have worked kind of quite fine without it, right? Because the optical coupling is quite strong anyway, right? So maybe that's a part of, because the rare earths will both couple to the phonon and the magnons, right? So anyway.
no, I agree with you. I think if you can localize the rare earth at the correct position in the optical mode or in the magnonic mode, I think you gain a lot, because you don't have your mode dilution problem, or your filling factor is getting better, or however you want to call it.
Yeah.
And this could really help. So this could really boost via the mode volume.
I think that there are always lots of challenges in this particular case. When I think about the phonons, they're operating in such a different space of metrics than the magnons. So typically, at least my recollection is that the bare coupling is typically a few hertz, and so you compensate by having lots of excitations in there to increase the coupling. And then the question is, how much can your material handle? which sort of pushes you to the nonlinearities. In the case of the magnons, the bare coupling is probably 10 to the 5 bigger, but the quality factor is 10 to the 5 smaller. So then the question is, do the excitations bleed over from one to the other as you try to impedance match? And so I think this impedance match issue in nonlinearity is going to be a key issue
I
I'm
think
worried about.
someone behind you.
So, okay, I'm not sure which part you were talking about. So so if you have resonant coupling between phonons and magnons, then the coupling is in the megahertz regime.
That's the direct coupling between them. I was sort of talking about the coupling to other excitations.
So to the optics, then but that's so if you want, that would be the advantage, right? That you can, so even if the optomechanical coupling is not, so the G naught is not large per se, you can pump and compensate for this. But still, the mode, so the impedance matching is it's an issue. So the mode matching, so the engineering of all, so that to get all the modes is such that at the end you have a reasonable chain is very difficult. So it might not, so you can think of other geometries that not need to be some, crystals or structure or some resonator with some optomechanical resonators, so to say, but still it's very challenging. I disagree.
Other comments, questions, signs of hope?
So that's the end of my list.
That sounds great. And, I think actually we've touched and we've explored all of the questions I would have brought up as well. This issue of, what is the coupling? What's the ideal coupling? So I wouldn't take it further. So, any other things people want to bring up in this general area? Because if not, we'll take some time for discussion, and I think coffee break at 3:30. So snack at 3:30. Let's thank Jevon.
Yeah.